Welcome here to another tutorial. This is Kliman. Today we'll be learning about solubility, equilibria, and the chemistry. And to those of you that are new to this channel, make sure that you subscribe on the YouTube channel and also don't forget to share. So we'll be doing solubility, equilibria, and our main goal is simply to know how to determine the KSP value and also how to find the concentrations and solubility of different chemical compounds. Okay, so when we're talking about solubility equilibrium, we're simply talking about two words. The first one is solubility. Okay, the first one is simply solubility. The second one is equilibrium. Okay, by solubility, what we simply mean is a substance or a compound that can dissociate or ionize itself in a particular liquid. Okay, a substance that can ionize itself in a particular liquid. If we talk about equilibrium, we talk about a substance that can reach equilibrium. Okay, this is just equilibrium. Okay, a substance that can equally dissociate and eventually reach equilibrium. Okay, so there are times where a particular molecule dissociates in water, then we determine its concentration. You might discover that the concentration might be at equilibrium with that of the molecule, that of the liquid in which it is dissociating. And that's the main idea of this particular topic, because usually we will be dissociating many molecules, many compounds, particularly in water or in some other solutions such as barium sulfate or sulfuric acid, whichever solution that we'll be using, it depends. But then there is something very important that we call the solubility product constant. Now, the solubility product constant, which is also referred to as the KSP, it is simply a value that tells us more about the level of dissociation of a particular compound or molecule. So, the KSP simply tells us the level of dissociation of a particular molecule. So if the KSP value is increasing, then we know that this molecule is capable of dissociating completely, or the extent of dissociation of this particular molecule is very high. But if the KSP is less, then we know that it will only partially ionize in that particular solution. All right, let's get started. Now, recall that a solution is one in which the solution is a saturated solution is one in which the solution is in contact with undissolved solid. Okay, so for example, if we consider a saturated aqueous solution like barium sulfate, then we get it in contact with solid barium sulfate. Okay, because the solid is an ionic compound, it is a strong electrolyte and yields these two particular molecules. Okay, barium ion and a sulfate ion. So what they're simply saying here is that if, for example, we look at the dissociation of barium sulfate, if we have barium sulfate, if we dissociate barium sulfate is supposed to be solid, we are going to get barium ion plus a sulfate ion. Okay, we're going to get these two ions. Okay, supposed to be 2 here. Now, this was in aqueous state. Now, remember that this was a solid molecule, but when it dissociates, it produces ions, and these ions, they ionize in water. So, in order for us to establish our KSP, we will concentrate mainly on these two same ions that have dissociated in the water. So we're going to say that our product, our solubility product constant, which is KSP, is going to equal to the concentration of barium ion multiplied by the concentration of sulfate ion, like that. Like that. Now, from this particular concept that we have here, we can therefore say that solubility product constant is simply the product. Let me use my other color. We can deduce that it is simply the product of this particular ion of its concentration to this particular ion of this concentration. Okay, so solubility product constant is simply the product of the dissociated ions. Okay, the ions that are produced when dissociation takes place. All right. Let me just try to wrap this. So that is just all about KSP, and we'll be using this particular concept all over. Now, we have this particular question. They're saying we write the expression for the solubility product constant for calcium fluoride. So now, in this case, the first thing to do is to imagine this particular molecule or compound as a solid. And of course, it's a solid. So in this case, we're going to say that calcium fluoride, solid, when it dissociates, it's going to form calcium ion plus fluorine. And of course, this remains in aqueous form. And if we balance it, we get a 2 here. So in order for us to write the equilibrium constant K, the solubility product constant, which is KSP, it will be the product of the concentration of calcium ion to that of fluorine. Now remember that we have 2 moles of fluorine, so we put our 2 moles. And of course, this remains our final answer. So that is how you write the solubility product constant. We proceed. Okay, it is important to distinguish solution carefully. Okay, especially between solubility and solubility product constant. Okay, so what could be the difference? Because there are times where a question is going to be given to you to find the solubility, and at times they'll ask you to calculate the solubility product constant. So the main difference here is that when you are dealing with solubility, you put your units in grams per liter. And of course, when you're dealing with solubility product constant, okay, just the solubility product constant, they will specify. You put your units in molar per liter. Okay, so whenever you hear they ask you to calculate the solubility, you put it in grams per liter, and of course, the other one you put it in molar per liter. So in this particular question, they're saying solid silver chromate. Let me just use my other. They're saying solid silver chromate is added to a pure water at 25 degrees and some of the solid remains undissolved. The mixture is stirred for several days to ensure that, remember what I was explaining about equilibria? Okay, so you'll be seeing this word oftenly. They're saying several days to ensure that equilibrium is achieved between the undissolved. Okay, so I've been given silver chromate, okay, and the solution. They're saying that analysis of the equilibrated solution shows that each silver ion concentration is simply 1.3 multiplied by 10 to the power -4 molar. Okay, so the first thing that we're supposed to do, we are going to dissociate silver chloride. Let's try to do that. Okay, so in this case, I'll try to write the dissociation equation here. So we have our silver, we have silver chromate, okay, so this is silver chromate, and of course we're supposed to, we have silver chromate. Okay, so supposed to have 4 here, and of course it will be in solid state. If we dissociate this particular compound, all right, let me just try to use something else. So if we dissociate this particular compound, we are going to get, silver ion like that, okay, in aqueous state, plus chromate. We'll get our chromate, and of course we put our ions like that, and of course this one remains in aqueous state. Now remember that we have 2 silver ions, so of course we put our 2 here, and everything remains balanced. Okay, so from here now we can write our equilibrium constant, we can write our solubility product constant. How is the solubility product constant going to be? Very simple. We use the same concept. So we're going to have our K. Our K is going to equal to the product of, this is silver ion to the raised to the power 2. Okay, and then we're going to have our chromate like that. All right, so we have written our expression. This is how our expression is going to be. Now we have been taught that we calculate The same we calculate the KSP for this particular compound Q. Alright, so how do we calculate the KSP? It's very simple. So we have our expression, so we're going to say that K, of course K is going to equal to, now remember that this concentration of silver has been given to be 1 point, okay, let me just try to wrap that. Right. So this is going to be, our silver ion has 1.3 multiplied by 10 to the power negative 4, then to the power 2 like that. Now remember that for chromate we do not have anything. So what are we going to do? We can calculate the concentration of chromate. How do we do that? We can use ratios. Let me show you. When you look at the equation, since the concentration of this particular molecule, this particular ion has been given to be 1.3 multiplied by 10 to the power negative 4 molar. So you're going to use ratios. You compare it with chromate, since they are the main ions produced. Like that. Silver has got 2 moles. Chromate only has 1 mole. Okay? Then you can put your molar. So we're going to have 1.3 multiplied by 10 to the power negative 4. Then we put our x. Then of course we're going to get 2x equal to, this is 1.3 multiplied by 10 to the power negative 4. And of course this is going to be over 2 over 2. Cancel, our x is going to equal to, okay, so if we do our calculations, what are we getting? Alright, so notice that our answer is simply 6.5 multiplied by 10 to the power 5 molar. So this is the concentration of chromate. So now, since we have everything, we can now do our calculations. Okay, so you take note of that value. So we now put our 6. Alright, sorry. So you now put our 6.5 multiplied by 10 to the power negative 5. Alright. From here, we can do our calculations. KSP is equal to, supposed to be SP, and of course SP. So if we do our calculations, we multiply this, don't forget the power. We are going to get our 1.1 multiplied by 10 to the power negative 12. And of course, this happens to be our final answer. So this is how you solve this particular question. It's very, very simple. Now we learn how to calculate solubility from KSP. learn how to calculate our solubility from KSP. They're saying the KSP for calcium fluoride is 3.9 multiplied by 10 to the power 11. So I think we can just write our datum. It's very important. Okay, so we have been told that our KSP in this case is just 3.9 multiplied by 10 to the power negative 11 at 25 degrees Celsius. Assuming equilibrium is established between solid and dissolved calcium fluoride and that there are no other important equilibria affecting its solubility, calculate the solubility of calcium fluoride in grams per liter. Okay, so for this particular question, the way we solve it is it's going to be very different, but we're going to do it in a very special way. Okay, notice that we have this particular compound. Okay, so we have this particular compound. So remember what I said in the first place? Very important that we dissociate it. So we have our calcium fluoride in solid state. If we dissociate it, we have calcium plus fluoride. That was more. And of course, write our 2 as the coefficient. Now from here, there is something that we are supposed to introduce, and that is called the ICE table. Why are we introducing the ICE table? Simple. Because we have only been given the KSP, but when it comes to calcium ion, we have not been given. When it comes to the fluorine ion, we have not been given. So it's better that we establish the IC table, and I'm going to show you how to use the IC table. It's very simple. So you write your IC table. I, this is for initial concentration. This is for the change in the molar concentration, and this is the equilibrium concentration. Now notice that in the IC table we do not consider anything that is liquid or solid. Therefore, we only put a slash to show that this is now, we don't have anything. Now in the first place, we haven't had anything to do with the concentration of any particular ion in this equation. Therefore, we are going to say that we in the initial reaction we only have 0 molar, and of course we have 0 molar even for the fluorine ion. For the change, we have now changed for the calcium fluoride because it is in solid state. But when it comes to the calcium ion, you check the number of moles for calcium. So the number of moles when this particular molecule dissociated, this particular compound, it produced this ion and this ion. But what is the amount of moles, the number of moles that this particular ion contains? You discover that calcium only contains 1 mole. Therefore, we say X. And of course, you don't forget to put your positive sign to show that it was favoring the forward reaction. In other words, there was an increase in the production of products, which are the ions. Okay, even here we do the same because we do have 2 moles, we'll say plus 2x. On equilibrium, it will still be now, but here we have our x, here we have our 2x. That is how you write your KSP. Now, notice that your equilibrium molar concentration, that is how you write your ICE table. Okay, this is how you write your ICE table. It's very simple. Now, notice that KSP is simply the product of the ions that have been produced. So we have our 2 fluorine here, and of course we put our 2. Notice that we have been given KSP to be 3.9 multiplied by 10 to the power negative 11. And of course, what is the molar concentration of calcium? Calcium is simply X. How about the molar concentration of fluorine? We have found 2x to the power 2. This tells you that a balanced equation is very important under this topic. Then you have your 3.9 multiplied by 10 to the power negative 11 equal to, okay, if we do our mathematics very well, we're going to have a 4 then x to the power 2. And of course, we have 3.9 multiplied by 10 to the power negative 11 equal to, so this is going to be 4x to the power 3 over 4 over 4. And our x cubed is going to equal to, let's try to calculate 3.9 multiplied by 10 to the power negative 11. Okay, then divide by 4. So we get our, it's giving me 9. This is supposed to be 9.75 multiplied by 10 to the power negative, this is supposed to be negative 12. And of course, we found our cube root. Our cube root. So our x is equal to, okay, let me try to calculate this. Okay, so we're getting our answer to be 2.1. 2.1, this is supposed to be 3. 6 multiplied by 10 to the power negative 4. Molar. Notice that this is not a final answer because the question is saying we calculate the solubility. And solubility is supposed to be in grams per liter. So how do we go about solving this one? Okay, it's very simple. In order for you to change everything to grams per liter, you're going to involve stoichiometry. So our molecule is simply calcium, fluorine. So calcium, this is 1 multiplied by 40. You find the molecular mass of calcium, and of course you get your 40.0 grams. Fluorine, Okay, so this is 2, so this is just 19 multiplied by 2, and of course we are getting now this is 2 multiplied by 19. I'm getting 38.0 grams. What is the final? Plus 40. So you get your 78.0 grams. So if you multiply this value, with this value, then you get everything in grams per liter. Okay, so we're going to say that (2.14) multiplied by 10 to the power negative 4 multiplied by 78.0. Your final answer, of course, is going to be 1.6 multiplied by 10 to the power negative 2. It's supposed to be grams per liter. Okay, so this is very simple. Okay, and if you want to show how the units are cancelling, this is what you do. So all right, so if you want to show, this is what you do. You have your 2.1 multiplied by 10 to the power 4. Okay, so this is supposed to be in molar of calcium flowing like this. So you know that of course this is under 1 liter of the solution. Then of course you are going to multiply everything by 78.0 grams of this particular compound over, this is supposed to be one mole of calcium fluorine, and of course these moles and these moles are going to cancel, and you are only going to remain with the liter and the grams. That is why your units are going to be grams per liter. Okay, so this is how you solve this particular question. This is your final answer. We get to some other things. Okay, so we look at the factors that affect solubility. The first factor that affects solubility, of course, is simply the presence of common ions, okay, which was simply called as the common ion effect, the pH of the solution, and the presence of complexing agents. So in case you are asked in one word answer, you have 3 marks for this. All right. Now look at the most important theorem under this particular topic, which is the common ion effect. So the common ion effect is simply that ion that is appearing on both sides. Okay, both sides when a particular molecule dissociates. So in this case, as we're able to see, we have calcium, we have fluorine, we have calcium and fluorine. We can say that calcium and fluorine are common ion effects, but there are times where you can dissociate this particular compound and you remain with a certain ion, and yet in the same solution while you are dissociating this compound, there were some other ions. Okay, so we'll look at some interesting questions on that, and we see how we can come up with what's this, what we're trying to talk about. So here they're saying that the presence of either calcium or fluorine in a solution reduces the solubility of calcium, fluorine, shifting the equilibrium to the left. And of course, this is very much true because because the more you are producing this, and this means that the more the concentration on your left is decreasing. So the concentration of ions is increasing, the concentration of the compound from which you are dissociating the ions from is decreasing. And of course, the equilibrium acts in such a way that it wants to return the disturbance back to its normal function. So because the disturbance is on the left hand side, the equilibrium is going to shift in this manner and simply support the left reaction. Okay. We look at how to calculate the effect of a common ion on solubility. They like bringing these questions and they'll ask you to calculate the molar concentration for different ions. So in this case, the question is saying we calculate the molar solubility of calcium fluorine at 25 degrees Celsius in a solution that is 0.01 molar of this is supposed to be calcium nitrate. This is what I was talking about. So sometimes they will ask you to calculate the molar solubility of a particular molecule, but then in the absence, you know that they've given you this. Okay? So the first thing to do, we use the same concept. We're going to dissociate this particular compound. So how do we dissociate it? Of course, when we say calcium, fluorine. If we dissociate calcium fluorine, we are going to get our calcium in aqueous form plus our fluorine. Supposed to be in aqueous form as well. And of course, we write our two for balancing just like that. Now, if you check properly, they are saying that from our data, we know that calcium nitrate, okay, so this is calcium nitrate. Calcium nitrate is composed of this particular ion. So we can just say that if we are to dissociate this particular compound, we are going to remain with calcium ion and the nitrate ion. In this case, we have calcium in the equation, and of course we have calcium in the equation, and of course calcium is the common ion effect. Okay, so this is our common ion effect. So this is how you come about with a common ion effect. We proceed. So the first thing that we're going to do, we're going to first of all come up with our IC table. So the IC table is very important. Why? Because we have not been given the concentration of calcium and that of fluorine, but we have been given the concentration of calcium nitrate. And remember, I think this will be necessary that I write it. We wrote our data here, and of course this is all right. Let me just wrap that, get rid of this Okay, so it's very important that I write that this is calcium nitrate. And we say we have two ions. This is the calcium ion, and of course this is the nitrate ion. But we said that this one is the common ion effect. So since in here we have this calcium and we have the calcium in here, it means that the concentration of this calcium in nitrate can also be related to this particular compound. So the relationship between this equation and this particular molecule is simply calcium. Okay? So from here, we can write our KSP, our IC table first. So the I for initial, we look at the change and the equilibrium. Now, of course, we know that this one is solid, so we say now at initial state, what was the concentration of calcium? It's not zero. Why is it not zero? Because there's a relationship between this calcium and this calcium here and this particular calcium here. Because it's the common ion effect, it's the one which is affecting the solubility. So in this case, whatever is the solution for this guy is going to be for this guy. Whatever is the molar concentration of calcium here is also going to be the molar concentration of calcium. All right. So at initial, our calcium is going to have 0.010 molar. And of course, we had nothing for the fluorine. Okay, so this was 0.0 molar. Notice that for the change, what was the number of moles produced? For the change, you only consider what you produce when you dissociate the ions. Of course, it is just 1 mole of calcium, and because the products are increasing, you put your positive sign, and of course you produce 2 moles of fluorine. And for the equilibrium, you already on the equilibrium part, let me make mention of this. You are going to have, since you had at initial stage you had 0.01 molar, and then for the change you have X. So here you are going to say that this is going to be 0.01 plus your X. And of course here, for the fluorine part, it will be 0 plus 2X, which is just your 2X, like that. Alright, so now we can wrap everything. So from here, notice that KSB is equal to calcium the concentration of calcium multiplied by the concentration of fluorine. And of course, we remain with our part 2. So our KSP was already given. Was it given in the question? Okay, so KSP, let me try to check. Okay, so we are using the same KSP. I think the KSP was given. we were using this same KSP here. So usually they'll give you the KSP. So our KSP is supposed to be 3.9 multiplied by 10 to the power negative 11. And that will equal to, have our calcium here. And we have our fluorine here. And of course, this is just the same as 3.9 multiplied by 10 to the power negative 11. That will equal to, we can now replace, so we have 0.01. This is supposed to be plus x. All over by, this is 2x, the power 2. Alright, so when we reach here, usually we don't really consider the x in such a situation. We don't consider this x. Why? Because this is a very small number. Okay, so we don't usually consider the x in this particular case. We leave it just like that. So we're going to remain with 3.9 multiplied by 10 to the power negative 11. That is going to equal to, alright, sorry. So, okay, that is going to equal to, supposed to be 0.01. Okay, so this is, then this is supposed to be 2x to the power 2. All right. From there, we can do our calculations. So we are going to have, this is going to be, of course, we're going to have 3.9. Okay, let me try to wrap. So we're going to have, so this is going to be 3.9 multiplied by 10 to the power negative 11 equal to, so this is going to be 0.01. All right, and everything being multiplied by, so it's 2x to the power 2, that is going to be 4x power 2. So that is going to be over by 4 multiplied by 0.01, and also here we're going to have 4 0.01. So if we cancel here, we're going to remain with x equal to, this is going to be, so this is supposed to be x equal to, then we can do our multiplication. So if we do our multiplication properly, we are going to remain with, so this is supposed to be 3.9 multiplied by 10 to the power negative 11. Okay, divide by 4 multiplied by 0.01. Of course, I'm getting, so this is going to be supposed to be 9.7. 9.75 multiplied by 10 to the power supposed to be negative 10 molar. So we find the square root that and that go that our x in this case is going to be, find the square root, we're getting 3.1. Okay, so we have 3.1225 molar. Okay, now in this case we have calculated for those two particular ions, but in this case all right, so we have our answer here. So this is just how you are supposed to go about this particular question. So in our next tutorial, I'll be able to show you just how to use the IC tables. Thank you so much.